Scott Kelly and Mikhail Kornienko have embarked on a one-year mission aboard the International Space Station to help gather more information about how being weightless in the space environment affects the human body. One area of particular interest is vision. Some of the station crew members suffer diminished vision after a long-duration mission, and a prime suspect is the shift of bodily fluids to the head during a mission. There's a new experiment known as fluid shifts that's looking to measure the shift and determine its impact on the crew members. Recently, my colleague Pat Ryan had spoke with one of the co-principal investigators on this experiment, Dr. Michael Stenger of the Biomedical Sciences Branch here at the Johnson Space Center in Houston, to learn about why fluids move to the head when you're in space and why that may be impacting astronauts' vision.
Well, on Earth, your body is designed to pump the blood from your lower body, from your big toe, all the way back up to your heart and into your brain, which is the most important organ to perfuse. When you go into space, your body no longer has to fight against gravity to do this. So you have this immediate shift of bodily fluids from the lower body up to the upper body. About 2 liters of fluid actually shifts to the upper body, which is why you see pictures of astronauts with puffy faces and engorged veins in their neck. And this is too much fluid in the upper body, and the hypothesis is that in your enclosed brain in the skull, which is a rigid container, that this increase in volume is leading to an increase in intracranial pressure, or ICP. And this increase in pressure is affecting the back of the eye. There are 2 holes in the front of your skull where your orbits sit, and this increased intracranial pressure is flattening the back of the eye, causing swelling of the back of the eye and the nerve sheath in the back of the eye, and ultimately this is leading to vision changes.
Because the eyeball is not the same shape.
That's one of the reasons, yes.
Well, so does it go back to normal then when they come back to Earth and the fluid is no longer shifting into their head?
And most astronauts it does. And shuttle astronauts, they experience these same visual changes. They carried extra glasses to wear on shuttle missions, but it's only been recently in long-duration missions that astronauts have been coming back with these visual problems that are not recovering. And so there's probably a length of mission effect here that's causing these permanent changes. So there are permanent changes, and we need to find out what's causing them before we spend even longer amounts of time in space.
Right. Now, what is your study called fluid shifts? What do you intend to find out, and how are you going to do it?
So we have 3 main aims in our study. The first aim is to fully characterize this fluid shift. So not only the amount of fluid that's going from the lower body to the upper body, but where this fluid is. We're going to measure fluid inside and outside of cells. We're going to measure fluid, blood fluid, plasma inside the blood vessels, and how this filters out of the blood vessels into the interstitial spaces. We're going to use ultrasound to assess total arterial blood flow into the brain, and then examine venous drainage out of the brain. So we want to fully characterize how this fluid is changing when you're in space. And our hypothesis is that different astronauts will have individual responses to this. And so there'll be different varying magnitudes of this headward fluid shift and subsequent redistribution of fluid. Our second aim is then to determine the relationship between those changes, the fluid changes, and impact on this visual syndrome. So we're going to examine non-invasive estimates of intracranial pressure changes associated with spaceflight. We're going to measure intraocular pressure using tonometry. We're going to examine the shape of the eye using ocular ultrasound to look at flattening of the back of the eye, any swelling of that optic nerve sheath. There's a really nice technology called optical coherence tomography, which takes these beautiful pictures of the back of the eye so we can see swelling of the choroid in the back of the eye, of the retina itself. And our hypothesis is that the more severe headward fluid shift that you have, the more severe these ocular structural and functional changes will be. And our third aim is kind of getting along the lines of this individual susceptibility issue. We think that pre-flight, by manipulating fluid shifts, by changing your posture, by assessing fluid location in your sitting upright, and then laying you down, then letting you head down to cause a headward fluid shift, and then applying lower body negative pressure to cause a footward fluid shift, we think that we can determine pre-flight individual differences in those responses, which may predict visual changes in spaceflight.
A susceptibility to the syndrome?
Exactly. And we also want to track astronauts post-flight for 6 months to try to understand better these mechanisms, why some crew members are recovering and some are not.
Now, much of the equipment that you described that you want to use is already there and being used in a related experiment, right?
Yes, the OCT, the optical coherence tomography, is being used in ocular health,
Right.
which is a surveillance study. We are flying some new pieces of hardware, some non-invasive intracranial pressure measurement devices. One is called the CCFP, and the other one is called the DPOAE. These are
What are those?
These are acronyms well, cerebral and cochlear fluid pressure is CCFP. DPOAE is distortion product otoacoustic emissions. These are non-invasive technologies that estimate changes in intracranial pressure by sending a sound wave into the ear, and there's actually a continuous fluid column between the inner ear and the brain called the cochlear aqueduct. And so if there's any changes in brain pressure, it'll change the shape of the ear, the inner ear. So by sending sound waves in and determining the characteristics of those sound waves as they bounce back, we can estimate changes in pressure. So we can estimate that while you're sitting up. And then when you lay down, the pressure in your brain will go up, so we'll see that change. And then if we apply an intervention, such as lower body negative pressure, perhaps we'll see that go back down again.
You mentioned that before, too. The lower body negative pressure suit, if you will, is a Russian piece of hardware that they've been using for years. How are you plan to make use of it?
So the Russians have this device called the Chibis. It's a lower body negative pressure, or LBMP suit. They use it as a post-mission countermeasure to sort of reacclimate the cosmonauts to Earth stress. So by applying a vacuum to the lower body, they can, in essence, suck the blood to the lower body as you'd experience if you're standing up on Earth. And so this stresses the cardiovascular system. At the same time, they're feeling a musculoskeletal stress. They've got suspenders on, so they're feeling pressure on the bottom of their feet. They're having to activate the muscles in their legs. And they use it to kind of reintroduce gravity, so to say, to cosmonauts before they land.
And they do exercise while wearing it.
Yes, they do. We're interested in that suction part of it. We're interested to see if this could possibly be a countermeasure to this headward fluid shift. By vacuuming the fluid back to the lower body, we're going to assess all these same parameters under this LBMP stress. So we'll look at blood flow to the brain. We'll look at drainage from the brain via the different veins coming out of the head. We'll look at pressure in the eye, pressure in the brain, structure of the eye, etc., while in the Russian segment. This is a somewhat technically challenging portion of the experiment because the Chibis is on the Russian side of the station, on the far end of the station. So we have to pack up all of our equipment, transport it to the service module, unstow it, set it up, use it, and then bring it all back again.
The findings clearly could have some impact on astronauts and their vision. Could findings be applicable to people on Earth too who have some kind of similar visual issue?
Absolutely. In fact, there are clinicians now that are investigating some of these non-invasive intracranial pressure devices for patients that have elevated intracranial pressure, such as hydrocephalus patients. And that'd be great for patients that have to measure ICP or intracranial pressure non-invasively, as opposed to an invasive measure such as a lumbar puncture. So it definitely could have benefits there.
Be very interesting to see how that goes. And is this going to be running throughout the year-long mission?
It is. The 2 one-year crew members are test subjects for this experiment, and they're the first 2, so we have 8 more after them.
More to come later. Great. We'll be interested to see what results you get. Thank you for bringing us up to speed on that. Dr.
Sure.
Michael Stenger is one of the co-principal investigators of the fluid shift experiment that is starting up on the International Space Station.